This is section 13.3 on the dot product. We figured out how to add, subtract, and scale up and scale down vectors in the previous sections, no matter whether they were two-dimensional or three-dimensional. Now we finally get to multiply two vectors together. It turns out there's two kinds of multiplication of vectors, though, and this is just the first of two. So it's not just vector products, it's the dot product of two vectors. What we'll do this section is you'll figure out how to do it. You'll figure out some properties of how the dot product works. You'll use the dot product to find the angle, which is the main thing that the dot product is useful for. That's such a simplification. That's the first thing that the dot product is useful for. Then we will project vectors onto other vectors, and you'll figure out what that's good for. Namely, it's good for doing work problems in physics. So let's get started. To find the dot product of two vectors, it's a little bit strange because what you would expect to multiply two vectors is that you would multiply them component-wise. So you would do the first component times the second component. And the second... Whoa, what did I say? That was not right. You do like the x component times the x component, and the y component times the y component. Because that's how addition worked. You just like added the x components and added the y components. But the dot product is something different. While you do multiply the corresponding components together, instead of putting the result into a vector, instead you just add them together. The end result is that u dot v is a scalar. It's not a vector. Sometimes the dot product is called the scalar product for that reason. The scalar product of two vectors. If you go deeper into math, you'll find out that there's something called an inner product, and the dot product is an example of that. So there's a lot of different words for these things. We will mostly call it the dot product, and you use a dot for this kind of multiplication. You end up with a scalar. So let's just see what happens. We immediately do some three-dimensional vectors. Of course, if you have 3 dimensions, you just do the corresponding thing. If you have three-dimensional vectors and you're dotting them, you multiply the x components together, multiply the y components together, multiply the z components together, and add them all up. This seems crazy, like why would we do this? And you'll see. At first, it's mainly because it helps us find angles. So let's just do it. U dot v here, you multiply the x components together and get 6. You multiply the y components together and get 0. You multiply the z components together and get -2. And then to get the dot product, you add these together. You don't drop them into a vector. So the dot product of these two vectors, which are like pointing in some directions, the dot product is 4. Whatever that means for now. Let's try v dot u. If you do v dot u, you'll do the first two components. You get the same thing. Because this is defined based on just multiplication of scalars is commutative, so this also is going to be commutative, the dot product. Let's get that written down here. The dot product is commutative. Are you familiar with this word, the commutative property? It comes from like a commute is where you go back and forth. And so the commutative property is flipping things back and forth. Two things commute if they go both directions. Okay, what else could we do? Given a vector, we could just dot the vector with itself. To dot a vector with itself, you do you would multiply the first components together. So you'd get 2 times 2. And then you'd multiply the second components together. That's 4 times 4. And then you'd multiply the third components together. In this case, that's also 2 times 2. Then you add together the results. So I'll get 4, 4, and 16. That's 24. How about the 0 vector dotted with v? Well, the 0 vector dotted with v, the 0 vector has 0 in all the components. And v has 2, 4, 2 in its components. So we multiply those together and add them up, and we get 0. So there's some there'll be some properties of dot products. it looks like multiplying, even doing the dot product with the 0 vector gives you a 0, the scalar 0. So the main thing to keep straight here is the data types, which is why I have these data types over my head. Vectors, usually we will have 3 components to them. It'll be 3 real numbers. When you dot 2 vectors together, you get a scalar, just a single number. What can you conjecture about the third answer? Okay, well, the third answer, what we did with the vector is we squared all the components and added them together. When else did we square all the, like here's the squaring the components and adding them together. We squared all the components and added them together when we were finding the magnitude of the vector. So the magnitude of the vector was the square root of all that stuff. So probably if you dot 2 vectors together, you get the same thing as the magnitude, except we're off by a squared here. So it looks like the v dot v came out to the magnitude squared. So I think we immediately write some dot product properties down. Yeah, good. So that'll be one of the dot product properties. For whatever reason, we're listing that as the 5th one here. Is that if you dot 2 vectors together, you get the magnitude squared. This looks strange because you would expect that if you multiplied 2 vectors together, you would get a vector, where over here you take the magnitude, that's a number. But no, both of these are scalars. The dot product gives you a scalar, the magnitude gives you a scalar, so it's possible for these to be equal. The other one we saw was that if you dot the 0 vector with anything, you get the 0 scalar. So there's a little arrow over 0, but not over this 0. The other things that we can write down as properties, we should point out that the dot product is commutative. The dot product also distributes, and I don't think I'm going to spend time proving these facts. I guess that one's like a little bit surprising, because this is not regular old multiplication. This is not like the multiplication of 2 numbers, but it still follows the distributive property. The other thing we can do is if you scale a dot product, that's the same thing as scaling one of the vectors first. So notice that like there's a distributive property of the dot product when it's like vector, vector, vector. This is not going to be a distributive property. These are all different kinds of multiplication. So instead you could think of it as like you could put the scalar on the u and you'd get the same thing, or you could put the scalar on the v and you would get the same thing. This is similar to how numbers work, right? If you were doing 2 times 3 plus 5, you could distribute the 2. But if you had 2 times 3 times 5, you wouldn't distribute the 2 here. You would say, well, you could do 2 times 3, or you could do 2 times 5. You shouldn't like multiply both. So this does not work. So same deal with dot products. So the dot product follows pretty reasonable like arithmetic rules. Let's do our first big application of like why we care about the dot product. It's really good at finding angles. So let's say you have 2 vectors, u and I don't know, v going this way, and you want to find this angle. To find the angle, we're going to want to use some trigonometry. So I want this vector as part of my world. And how do we get here? Like what vector is this? Well, it would be you start at v, add something, and end up at u. So it's like v plus what is u? And the answer is that that's u minus v. So this vector, to complete the triangle, is the vector u minus v. Then we can say, okay, I know like some facts about triangles, and in particular, the one I'll use here to get at this angle is the law of cosines. I wonder if you remember the law of cosines. I don't know if you do. Probably not. Maybe? I don't know. It's basically that you can write down the Pythagorean theorem, And it's true for any triangle as long as you deal with the fact that this angle is not a right angle. Like if this angle is a right angle, then you're just good and this is true. But if it's not a right angle, you have to subtract 2ab cosine theta. So let's use that on this triangle. C is the magnitude of u minus v. A is the magnitude of, let's say, u. B is the magnitude of v. And we'll drop in a and b in here too. So we'll have a squared plus b squared minus 2ab cosine theta. So here's an equation, and this is just a trigonometry equation. What I'm hoping to do here is get something having to do with the dot product to appear so that I can use the dot product to find the angle. How will we do that? Well, using this fact, which is that anytime a magnitude appears, you can turn it into a dot product if you want to. So magnitude of u squared, that's u dot u. Magnitude of v squared, that's v dot v. Please try to pay attention to the data types here. If you're into computer programming, you're probably used to that like you have to keep track of what kind of object each thing is. But like u dot u is a number, it's a scalar. So is magnitude of u squared. This one, it doesn't have a squared on it. Oh, it's supposed to have a squared on it. It's this one. So this one is u dot v, or u minus v dot u minus v. So what can we do here? Well, I can basically FOIL the left side. Because I have the distributive property, this one, it lets me FOIL a bunch of vectors. So I'll do that. I'll have on the left side u dot u minus outside u dot v minus inside v dot u plus last v dot v. That's the left side. And then the right side, let's just keep the right side as it was over here. What can we do? U dot u is here on both sides, and so is v dot v. Those are gone. U dot v is the same thing as v dot u. So I have actually over here minus 2 u dot v. And on the right side, I have minus 2 u v cosine theta. If I solve for cosine theta, well, okay, divide by minus 2, and then divide by magnitude of u, magnitude of v, and I get the formula for how to find the angle between two vectors. You take u dot v and divide by their magnitudes. It's kind of awesome. So the angle between two vectors is given by, well, it doesn't tell you the angle directly, but it tells you the cosine of the angle, which is good enough. It's u dot v over the magnitude of u times the magnitude of v. Awesome. Let's do it. Actually, let me make a note first, which is that if you had turned u into a unit vector first by normalizing it, and then you had turned v into a unit vector by normalizing it, then you could just dot the two unit vectors together, and that would give you cosine theta. So this is the formula that we'll use most often because we often don't have unit vectors. But if you happen to have two unit vectors, you can just dot them, and that gives you cosine theta, which is nice sometimes. Okay, let's find the angle between these two vectors. We're looking between the vectors 3, 0, 0, and I'll call that u, and 2, 2, 0. There's no k in here, so the z coordinates are 0. Well, how do I find the angle between them? I just use this formula. I say that cosine theta is u dot v over magnitude of u, magnitude of v. So let's do it. U dot v is multiply the x coordinates multiply the y-coordinates, multiply the z-coordinates, and add them together. Magnitudes are square all the components and take the square root. For this first vector, its magnitude is 3. For the second vector, well, I can't immediately tell, so I'll square all the components, add them together, and take the square root. So in total, what do I have here? The numerator is 6, the denominator is 3 square root of 8. It's kind of ugly. Okay, square root of 8 is square root of 4 times square root of 2. So that's 2 square root of 2. And then 3 times 2 cancels with 6. So I actually have cosine theta is 1 over the square root of 2. I know that angle. That angle is 45 degrees. Or pi over 4, whatever you want. So these two vectors, where one of them points directly out in the x direction and the other one is like a little bit x and a little bit y, maybe it's like this way, they're at a 45-degree angle. And you can just find that using the dot product. It's very powerful. I like it. Okay, let's do these two. I'll call this one u and this one v. Again, you just write down the formula. Do you get this? I mean, you've taken a lot of math classes. I think you get this perspective that, like, we want to both see that the formula comes from some simple fact. Like, I want to see the law of cosines create the formula, and I want to just use the formula after that. Like, I don't want to prove it using the law of cosines every time. So I'm not going to use the law of cosines anymore. I just kind of remember that this formula is the law of cosines. It's u dot v over magnitude of u, magnitude of v. Dot the vectors together. So that's multiply the x-coordinates, multiply the y-coordinates, multiply the z-coordinates, and add them together. And then divide by their magnitudes. The magnitude of u is square all the components and add them together and take the square root. And the magnitude of v is do the same thing. So in total, on the numerator, I have minus 12 plus 4. So that's minus 8. In the denominator, it looks like I have square root of 14, square root of 20. Does anything good happen here? I've got like 2, 7, 2, 2, 5 as my factors. So these can come out. So cosine theta is minus 8 over 2 square root 14 square root of 5, because I can get the 2 out from square root of 20. So I can cancel the 2. The denominator, just nothing really good happens here. I get 50 and 20, so it's the square root of 70. I don't know any angle theta that has this cosine. I know that if the cosine of the angle is negative, I must be in the second quadrant, so it's like an obtuse angle between these two vectors, but the only thing I can really give you is that theta is the arc cosine of this weird number. And that's my answer. Okay, depending on what angle you get, it tells you certain things about the vectors. So like if the angle comes out to 180 degrees, that means that the vectors are pointing in opposite directions. They're opposing vectors. If the angle is 0 degrees, then they're pointing in the same direction. They're parallel vectors. And if the dot product of two vectors is 0, then that means that either, well, like if the dot product is 0, that means that one of these things must be 0 also. So one of these must be 0. So basically either one of the vectors is the 0 vectors, one of the vectors is just the 0 vector that's not pointing in any direction. Or the cosine of the angle is 0. That means that the angle is pi over 2. This looks like kind of like a side fact that we're doing just in the middle of the section that's like randomly here, but it turns out to be the most important and most commonly used application of the dot product. If two vectors have an angle of pi over 2, that means they're perpendicular to each other. And when we have two vectors that are perpendicular to each other, we have a special word for that. It's called orthogonal. Ortho is like right, like straight, like right angles. So this is the most common use of the dot product. If you ever want to show that two vectors are perpendicular to each other, and two vectors being perpendicular is called orthogonal, then you'll use the dot product. If the dot product comes out to 0, you've got orthogonal vectors. This is just a side note for now, but you would generally say that if your two objects that were perpendicular, like say the surface of my forehead and this pen, neither one of them is a vector. And so I would say that these two, the surface of my head and this pen, are normal to each other, where two vectors that are perpendicular, I would say they're orthogonal to each other. And we'll deal with the details of the terminology later, but just try to get the terminology correct. So how could we ever get two orthogonal 3D vectors? Well, it doesn't matter. You can just write whatever you want for the vectors. Let's say 1, 3, and then let's like see how to make it orthogonal. Right now, the dot product of these vectors is 3 times 1 plus 4 times 3 plus 5 times, I don't know, and I want it to come out to 0 to make the vectors be orthogonal. Can this happen? Sure. You can always fill in the last component to make the vectors orthogonal. You just make the dot product come out to 0. I guess minus 3. 3 plus 12 minus 15 is 0. So here's two vectors that are orthogonal to each other. They're not like in the xy plane, they're not like the coordinate axes, but they're in some other directions and they're orthogonal to each other. So that's the end of the basics of the dot product. Now we'll get into a little bit more complicated things, but I just want to stress one more time that this part of this section should kind of be like glowing or something. That the main application of the dot product is to show that two vectors are orthogonal to each other by dotting them and getting 0. Okay. The last application, which I think is like 2.5 pages or so of these notes, is what are projections good for? And we will end up writing a projection using a dot product, which is why it's in this section. So what we do is we say, first, this is usually hard for students to read because it's got a subscript of a v, and then the thing is the u. The way that you can remember like what's going on here, how to read this, is that the u is in the place where it's like the input to some operation. So whatever is going on here, it's being done to u. So it's the something of u. And that's why this proj v u is the projection of u onto v, because like it has to have this, because u is here. So given a vector u and a vector v, you can project u down onto v by thinking of v as like the floor, and you shine a flashlight on u perpendicular down at v and see what you get. What you get in this case is you'd get like the shadow of u on v would look like this. And this is the projection of u onto v. There's lots of different projections. You can project onto various things, but the projection of u will have u at the end here. So this is, what is this good for? Say you have some effect that's happening in the u direction. It's usually like a force. It could be like the wind. And you want to know, does it push you, what does it do in the direction of v? So say you're like walking in the direction of v on a road, and you want to know if the wind blowing in the direction u helps you or hurts you. Well, you take the projection of u onto v, and that's the amount that it helps you or hurts you in walking in the direction v. So it's like the effect of u in the direction v. Okay, let's calculate it, and then we'll do a physics example at the end. So let's just graph a couple things to get a good picture of what projections look like. We're going out to 10 here, so I guess we're going to say this is 2, 4, 6, 8, 10. The vector u is 5, 10. So it goes over 5 and up 10. The vector v is 4, 3. So we'll go over 4 and up 3. Then we'll start projecting stuff. So the projection of v onto u. Oh my gosh, I read it wrong. Okay, maybe beating myself up is unproductive here. But this is the projection of u onto v. I just spent like 5 minutes explaining why it's that. Well, so this is v. This is u. If we're projecting u onto v, then we say, okay, well, here's the v direction. How much does u go in the v direction? And the answer is you like shine the light down perpendicular to the direction of v. And this is the projection of u onto v. If you instead shine a light on v and see how it projects onto u, well, that's okay. You can do that too. You think of u as being the floor, and you shine a light perpendicular to that to see how v contributes in the u direction, and you get this. This is the projection of v onto u. What are the relationships between them? Well, if you project onto v, you end up parallel to v. And if you project onto u, you end up parallel to u. But you could see that in the flashlight picture. This final picture is a total mess, but luckily you can rewind and see it being built. Okay, so here's the summary. The summary is that the projection of u onto v is written this way, is the vector that's like, what's the effect of u if you are restricted to it working in v's direction? And then, yeah, the other way. The other way is the other direction. What can we actually do with these? Oh wait, that's not what's being said here. Oh my gosh. Okay, so here's the projection. Let me redraw this. Here's u. Here's v. It wants the projection of u onto v, so that's like this. Projection of u onto v. And then the vector component of u orthogonal to v. Okay, that's, I'm out of colors. That's this one. This is orthogonal to v. I guess the point of this box is just that you can think of u as being made up of two components, the part that's in the direction of v and the part that's perpendicular to v. Normally we think of a vector as having two components, like the x component and the y component, but technically the projection lets us think of it as having like a v component and a not v component. I don't remember why this information is in this box like right now, because it doesn't, I don't know. Oh well. Okay, let's get a formula for the projection so that we can actually find it, and then we'll use it in a physics problem. So as you can probably guess, the plan here is going to be to draw a triangle. So I'm going to get u, and we'll get v here. And just to make the picture easier, I'll have v be going horizontal. Now, what is the projection of u onto v? You think of this direction of v as being the base, and you say, well, how much does u contribute in that direction? This is the projection of u onto v. Okay, I want a formula for this. So how am I going to get this? Well, I know that this projection is going to be some multiple of v. So we know the projection, is some multiple of v. And the question is just like, what multiple is it? Then we've got this vector here. This vector, can I do the same like subtraction trick? Yeah, u is the projection plus this question mark, whatever this is. So this question mark must be u minus the projection. What we've got here is a nice right triangle, so hopefully that will allow us to like make everything work out nicely. Small cut there, but now we're back. So we have this right triangle, and what you would expect is that we would be able to use the Pythagorean theorem to make this work out nicely. But we have like this new insight about what right angles are good for. Right angles, the best way to write down a right angle now, like the fact that an angle is a right angle, is using the dot product. So whenever you have a right triangle, instead of saying, well, I only know one fact about right triangles, it's the Pythagorean theorem, it's pretty safe now to actually say, well, I only know one fact about right triangles, and that's that the dot product of the two legs is 0. And that's like much more powerful. So let's see how that works. How that works is that these two things need to be perpendicular to each other. So the projection is perpendicular to u minus the projection. Remember, the goal here is we're trying to get a formula for the projection. So since these two things are perpendicular, that means that their dot product is 0. It like turns a geometric fact into an algebraic equation. It's really good. Okay, we already wrote proj v of u is this constant times v, so let's substitute that in. You'll notice that as soon as I started to have objects in my equation that were where some of them were scalars and some of them were vectors, I started clarifying by putting an arrow over them. That's just an instinct that you'll need to develop over time. Every object earlier was all vectors, so I wasn't bothering to do that. Like, I don't need to label every single thing with an arrow if everything has an arrow. But now C is a scalar, so I'm putting arrows over things that are vectors to make it more clear about what's going on. Okay, we have a distributive property of dot product, so let's use it. We get that we can have the left side as cv.u minus cv.cv. My notes are wrong, but I'm pretty sure this is right. It's pretty convincing. Let's start by dividing. Can we divide everything through by c? I guess so. Just be careful here that this is all multiplied together. So when I divide through by c, I'm going to have v.u minus, and then there's still a c here. Cool. Okay. We have a formula for v.v also from earlier in the section, and then this is commutative, so let's just write it in a nicer order. So I'll have u.v minus c, and then the dot product of something with itself is its magnitude squared. So what's the point of this? Well, if I'm trying to figure out what the projection is, so I'll just solve for c. Get the c term over on the right, and divide by magnitude of v squared. This is my scalar c. It tells me what is what is the multiple of v that u contributes. It's this thing. So that means that we can actually use this as the scalar right here to make a formula for the projection. So this will be our formula. The projection of u onto v is a multiple of v. But which multiple of v? Well, this one. This multiple. U dot v over magnitude of v squared. It's a little odd to put arrows over everything again. I guess I don't want to. Oh well. Keep track of the data types here. This v is a vector, and this whole fraction here is full of vectors, but it's a scalar, because the numerator is the dot product, which gives you a scalar. The denominator is the square of the magnitude, which is a scalar. So this fraction is all a big scalar that tells you how to scale up v. But this is the projection formula. Okay, let's do some projections. We're doing the projection of u. So to get that started, it's projection of u. But then what are we projecting it onto? That's this. Projection of u onto v. Okay, well, I have a formula for that. It's u dot v over magnitude of v squared times v. Oh wow, my instinct of when to put vector arrows and when not is a little bit messed up here. Everything is vectors here, but I was imagining, no, this is the vector and these make a scalar, so that's why I put an arrow here. There's no fixed rule about when to draw the arrows. Let's do it. U dot v is you multiply the corresponding components together. So 4 times 3 for the x components, 1 times 4 for the y components, and add them together. The magnitude of v squared is the same thing as v dot v. So you can just dot this with itself. You get 3 times 3 and 4 times 4. Then v is just the vector v. So what we'll end up with is the vector v with a scalar multiple. Let's see what the scalar multiple comes out to. This is 12 plus 4, so that's 16. This is 9 plus 16 is 25. So the projection of u onto v, let me distribute this scalar in. We'll get 48 25ths and 64 25ths. Is it really called distribute? Distribute is the wrong word. Let me scale the vector. You use the word distribute if you have a multiplication and an addition, and you're using like one to distribute over the other. There aren't two operations here. There's just a scalar multiple, so you shouldn't call it distributing. Anyway, this is the projection of 4, 1 onto 3, 4. That's nice. Who cares? First, let me emphasize that the main thing we will use dot products for in the future is showing that vectors are perpendicular to each other, which is called orthogonal. And then later on, we'll have more complicated objects and we'll show that those are perpendicular to each other, and then they'll be called normal. So that's the main use of vectors, is to, if the dot product is 0, then they're perpendicular. But this is an easy, immediate benefit, is like, how do we use it to calculate work? Now, the reason we would need to use a dot product to calculate work is, say you have a box and you move it, there's this easy formula that the work is the force times the distance. This is because like force might be in like newtons and the distance might be in meters, and then a newton meter is called a joule. So this is how the units work out. So if you take a box and you like drag it a certain distance by using a certain force, then you multiply those to figure out the work. The problem is when you're like pulling a box, you usually don't just pull it directly horizontally. If it's like a box that's on the ground, you'll have maybe a rope or something tied to it and you'll pull, but you'll pull kind of like up and to the side. So if you're pulling this way with some force vector, the issue is that the effect you're having on the box, you're not actually like picking it up and launching it into space. It's actually staying on the ground. The only effective work that you're doing is in this direction. And so you want this vector as the actual force vector that you're using to calculate. So this is the effective force. So the work that you do Well, it's like you need to like you want to multiply the force times the distance, but you don't want to use all the force that you happen to be exerting. Only the force that's like effective in the direction that you're pulling it. So instead of doing the force times the distance, what you'll do is you'll use a projection of the force onto the direction you're actually going. I don't know, I'll call it PQ. Where like this is where P is and this is where Q is. So you'll replace the force vector with like the actual component of the force that's going in the direction you care about. Let's see it in practice. So let's say you've got a wagon. Nice wagon. We're going to pull it 20 feet. And we're going to pull with a force of 30 pounds. The problem is the force is going to be 30 degrees from the horizontal. This time the units, instead of being newtons times meters, is going to be pounds times feet. And we don't have a fancy name for that. Those are called foot-pounds. This will be our unit of work at the end. It seems like you're exerting 30 pounds of force and you're pulling the wagon 20 feet, so you should just multiply 30 times 20. But actually, no, you should not do that. Instead, you should project this vector down onto the direction that you're actually worrying about, which is this direction. So instead of 30 pounds times 20 feet, you say, no. I want to project down and use this 30 degrees. So it's going to be 30 cosine of 30 degrees times 20 feet. Where did the cosine come from? Well, if you ever have a triangle like this, and you know its hypotenuse, see? Then the projections in the various components, this one is the horizontal component, which is cosine, and this one is the vertical component, which is sine. If you set up the triangle this way, then the sine of this angle will be c sine theta over c, which is sine theta. And the cosine of theta will be c cosine theta over c, which is cosine theta. So this schematic picture makes it easy to do this problem without using the crazy projection formula. This component of the force is 30 cosine 30 degrees, which is right here. So what do we get? Cosine of 30 degrees is square root of 3 over 2. So I get 300 square root of 3 foot-pounds. Cool. Okay, so what's the summary of what dot products are good for? The main thing is you dot two vectors together and you get a scalar. And the main reason you would care is that if that dot product comes out to 0, it means that the vectors are orthogonal to each other. A secondary reason you care about the dot product is that you can use it to project vectors using a kind of scary looking formula, this thing. But the scary looking formula is not hard to implement in practice as long as you can keep straight what this notation says, which is it's the projection of u onto v. Finally, this would come up most often in a physics situation if you had a force that was not actually going in the direction of motion, and then you would do a projection to figure out what the amount of force actually is that you care about. So that's section 13.3. Do some homework. Ask me some questions.